In the beginning, at the dawn of time, we all did this manually. We got staging machines, we did some stuff, and it was great, except it was not great. It was slow, error-prone, and time-intensive. Over time, we got new tools, things like Fabric, Chef, Ansible. They help to automate things. We got a whole container ecosystem with Docker that helped to automate things even more. So with the rise of new tools, that was a challenge.
Am I live now? Awesome. All right, so with the rise of new tools came new challenges. So let's set the stage. My main application is a fairly standard Django monolith. We're still on Python 2, but that's not really relevant for deployment. We've got Celery for background tasks, channel for WebSockets. We're using Postgres for the SQL database, and we use Redis and RabbitMQ. Additionally, one sort of complicating thing is that my main application is single tenant. That means we deploy one instance per customer. Mostly this just means that we have all the same problems as everyone else, but much more so because we have to deploy a lot more environments. So whereas most people would have, a couple of dev environments, a couple of QA environments, one staging and one prod, we have a dozen or two prods. So this leads into what our old deployment system looked like. There were two main pieces, Terraform for setting up all the stuff on AWS, and then Ansible for configuring the systems and deploying the actual application code, along with some Python scripts for things that didn't fit into either of those. This was a good system. Secrets lived in Ansible Vault, access control was managed via SSH key distribution, pretty solid all around. But there were some downsides. Setting up a new instance took an hour or two of work overall, running a whole bunch of Terraform stuff, making sure that everything was all up to date, dealing with bugs that had creeped in since last time we did it. And that hour had to be someone on my team. Similarly, scaling up and down, if we needed to boot a new web server, that took a little while, and we really couldn't even think about doing auto-scaling. So good, but not great. We also have a bunch of microservices, but I'm not going to talk about those for this talk. So we had some constraints for what we wanted to build as part of the new system. We knew we wanted to use Kubernetes. We'd already been using it for some other projects, and it's my weapon of choice for container wrangling overall. Additionally, we wanted to keep using RDS and Cloud AMQP for databases. I'm probably more in favor of running databases on Kubernetes than most people, but I do have a very small infrastructure team, and so I will basically always trade money for not having to worry about databases. Also, that would make the production migrations easier because we didn't have to move any data around. What do I mean by a forklift migration? This means I can make changes to the application, but not like a greenfields rewrite everything in Go and make everything glorious. We had an application. We wanted to pick up the entire application basically the way it was and just drop it into Kubernetes. Before I start talking specifics about my application, let's define some jargon for people that haven't heard it before. Two generic terms. A container is a cool way to run a process, and an image is the larval form of a container. Kubernetes is many things to many people, but for the purposes of this talk, Kubernetes is an API for making containers jump through hoops to do useful work. And pod is a container-specific term that every time you hear it, you can basically just pretend that I said the word container. So with all that laid out, I was ready to roll up my sleeves and jump into porting my application to Kubernetes. First step in containerizing any application is to make a container image. Multi-stage builds are super useful for Python applications because Python apps usually have much bigger build time dependencies than runtime dependencies. One thing of note here is the fact that I'm not using a virtual env. Some people will disagree with me, but I don't really see the point in using a virtual env when it's a single-purpose container in the first place. So here's our build image, and then our run image. So we ran the build phase first, and then we copy over just the files we need into a much smaller run image, along with setting up a non-root user for the application to run as, and anything else that's sort of runtime specific. My first attempt to get things set up in Kubernetes was very, very simple, just static Kubernetes manifest YAML, no automation beyond kubectl apply. Fitting an entire Kubernetes YAML file on screen is really not going to work, so here's just sort of the core of it, but it gives you a general idea. Start up the container, mount up a configuration file. We put all our configs in YAML and then read them in the settings.py. Run some migrations, and then launch Unicorn. Pretty simple, like these are all the steps that you'll probably have seen a million times, just done inside Kubernetes. A quick improvement from there was to move the migrations from being run just sort of as part of the main container into a thing called an init container, which only runs the first time a pod is launched. For some bonus points, this sort of shows a very easy way to do some dynamic configuration injection, again, using init containers. But this still had a lot of issues with ordering. Init containers run every time a pod starts, including every time you launch another replica of the pods. If we wanted 4 web servers, it would try to run the migrations 4 times, which isn't really what we want. Django migrations are generally safe to run more than once, but you can get some weird locking issues and things like that. It was just not a good scene. We also had issues where, like, because we weren't running the migrations first when we were upgrading Celery, it would roll out the new code before the migrations had finished, and everything would get really confused. So good start. This proved that we could run our application under Kubernetes, but we clearly needed a more organized deployment system underneath it. A few things I glossed over, just so we're keeping track of them. The other three main daemons work exactly like the DjangoCon pods. They just run a different command. Instead of DjangoCon, it's running Celery or DEFNA or the channel worker thing. We build all of the daemons into the same container image, as opposed to building separate images for each one. This was mostly because the shared dependencies are so much bigger than anything that's specific to web or Celery or channels that it made release management a lot easier to have one release artifact instead of 4. I'm also ignoring Celery for right now. We will get to it later. My application is mostly an API that's used by mobile applications. So we do have web interfaces in it, but they're mostly either used rarely or used by administrative staff. So I decided to keep things simple and try to avoid using S3 for the static files. For things that are dynamic, like user uploaded media files, that still has to go in S3 because you need a shared system of some kind. But for the actual static files, we build that into the image and we serve it using a cut down version of the Caddy web server. So that just means that we don't have to separately deal with versioning the static assets and the deployed image. And for the initial phase, I was going to sort of start with RDS, because we know that's what we wanted to use in the end, but launching and destroying an RDS cluster takes about 30 minutes, and that was getting really annoying for rapid development. So we did most of the initial phases of prototyping using Zelando's Postgres operator. So by this point, I had a working proof of concept. I could deploy my entire stack on Kubernetes and use the application. The application itself worked like normal, but deploying it was still not really great. We needed something that was more repeatable and reliable. So, next tool in standard Kubernetes quiver is a thing called Helm. It calls itself the Kubernetes Package Manager. This is overall fairly similar to what we had before. The idea is you just take the existing static manifests, you dump them into a Helm chart, and then you can install that chart as many times as you need with different inputs. I'm not going to go over the chart itself because it's basically the same thing we saw before, just more curly braces. But overall, Helm did improve some things. It made deploying multiple environments way easier. We could store just the values that had to vary between the environments in YAML files and feed them into Helm. That part was great. It's also widely supported by basically everything in the Kubernetes ecosystem because it's such a standard tool. And we had some operational experience with Helm from other projects. But it also brought some problems. It basically doesn't help us with the ordering and sequencing issues we had with migrations and things running out of order. It does have a thing called hooks that let you kind of do what you would think, like before I deploy, please run the migrations. But we ran into no end of problems with it. Error handling wasn't great, debugging wasn't great. And in the end, we just decided that it was too complex to work with for that function. There's also some major gaps in the Helm ecosystem. Unit integration testing of Helm charts is basically impossible, and secrets management exists, but is basically delegated to plugins. And then the big problem with Helm, Tiller. I'm not going to talk a ton about this because they have already released a beta of Helm 3, which removes Tiller, but the rough version is it's a security nightmare. It's a single point that all requests have to go through, and everyone gets access to whatever permissions Tiller itself runs with, which is usually the cluster give me all permissions admin role. They are removing this, so it's going to get better, but it's not there yet, and all of the workarounds for not running with Tiller have various downsides that we didn't love. So okay, Helm worked. We could use it, but it wasn't quite as smooth as we wanted it to be. We had a lot of problems with what happens if there's an error during deployment. How do we deal with that? And it made self-service fairly tricky to set up because of the permissions issues I mentioned with Tiller. And so with that, we have our current and hopefully final approach, a Kubernetes operator. This is going to be the bulk of the rest of the talk. Kubernetes operators tie together three main concepts: CRDs, watches, and controllers. Let's go over each of those. A CRD, or custom resource definition, is a way to add new object types into Kubernetes. Just like pods and services exist in Kubernetes, we can make our own. In this case, we call it Summon Platform because that's the name of my Django monolith. It lets us add a new object type, and we can add whatever fields and parameters we want on that, just like any other object in the Kubernetes API. In this case, you can see we have a version field, which takes a string of what version we want to deploy, and we have a config thing that takes a dict of some Django settings, in this case, just turning debug true. This is a bit more verbose than a Helm values file for anyone that's worked with those, but it does allow for some nice things, like you can have type validation on your variables, which is a thing that Helm itself does not natively support, and you can use tools like kubectl apply with this directly as opposed to having to go through multiple intermediary tools. So the CRD gives us a place to put all of our configuration. It holds the data for what we want to deploy, what we want our configuration to be, all that kind of stuff. But now we need to actually do something with it. And the driver for those are a thing called an API watch. It's basically like push notifications for the Kubernetes API. Whenever an instance of my custom object changes or is created or is deleted, I want to get a notification in my code so that I can do something with that new data. or lack of data if it's a delete. The heart of an operator is a controller. Each controller sets up some API watches, waits for a change, and then does its best to make sure that the state of the world reflects the new config, repeat indefinitely. That's what an operator or what a controller is, sort of deep down in the heart of an operator. Before we dive in to talk more of the specifics of our Django controller, let's pull back a bit and talk about building convergent systems. And before we do that, let's pull even further back and talk about the opposite, which is procedural systems. A procedural system is built by giving the system all of the steps that you want to run in the order you want to run them, like, say, a bash script. That is the steps that you want the code to take in the order you want it to take them. Real simple, easy to write, as opposed to a convergent system where we don't tell it what steps we want it to take. We just say, this is the state that I want the system to be in when you are done. Figure it out. So if you've worked with Ansible, for instance, it is a convergent system. You don't tell it what steps you want it to take. You say, this is what state I want the system to be in when you are done, and it figures out what it has to do to get there. Very briefly, two other important concepts that I'll be mentioning throughout this. Idempotence, or a system being idempotent, means that it only takes action when it needs to correct the state of the system. So going back to the Ansible example, if you tell it you want a package installed and the package is already installed, it doesn't try to install it again. That's all it means. Long word, simple. Promise theory is a mathematical framework for designing convergent systems by breaking them down into smaller subsystems that adhere to a specific contract of, you give me this data and I will try to make the state like that. Promise theory systems can work at several levels, so we can start with small promise theory actors and compose those into bigger actors and compose those into bigger actors. In practical terms, this means taking the thing that you want to do, in our case deploying a Django app, and trying to break it down into multiple smaller convergent bits that can each be built and tested independently, which helps to reduce the surface area of your actors and keeps the code a lot more manageable. So we don't write a single giant function that does everything. Instead, we write a small object that creates a RabbitMQ vhost, and a small object that creates an S3 bucket, and then we use those in building our deployment. Just like, again, I keep harping on Ansible because it's the thing most people here have people have most likely used. When you're writing a role, you can compose that out of other roles. Why does all of this design and theory matter? Because part of being successful with Kubernetes or any convergent system is to rotate your thinking from procedural to convergent. You might have noticed that my brief description of promise theory lines up very well with also how I briefly described Kubernetes controllers, and that's no accident. Kubernetes uses these patterns because over the last decade or two, we figured out that when you're managing big, complex distributed systems, it is far better to work with a convergent system than a procedural one. The real problem deep down, and we'll talk more about this a little bit, is state drift. Failures happen. Like, there's going to be errors during deployment, and after that error occurs, you don't really know what state your system is in. You could go and find out and try and correct it, but that's very time consuming. And if you've got, say, just like a big bash deployment script with like rsync and a whole bunch of stuff, a lot of people have written those, I've definitely written those. But unless you account for every possible starting state, if the system is in an error state of some kind and it's in some weird configuration, your script may just break randomly. Like, you're trying to rsync and the destination folder doesn't exist. What's it gonna do? It doesn't know how to deal with that. But if you are building a convergent system and you just tell it that folder must exist, no matter what errors kind of go on, it'll make it right and it'll eventually get you to the goal state. So controllers can be used for all kinds of things, but most of them in Kubernetes follow this pattern. On any change to an object, read that object in, generate a whole bunch of other Kubernetes goop, apply that into the Kubernetes API, or sometimes like talk to external systems, so like the one that makes S3, instead of talking to the Kubernetes API, it talks to the AWS API. And just loop this forever. So every time there is a change, you get the object, you read what was requested, like I want an S3 bucket called foo, and it should have permissions public. Talk to the AWS API. If the bucket doesn't exist, create it. If the permissions don't match what was requested, fix them. Repeat forever. This loop ensures that everything gets rebuilt effectively from scratch. So if we are just sort of running and I go and delete that S3 bucket, the next time it reconciles, it'll just recreate it. The system doesn't have to care about what error state things were in. All it wants to do is know what is the current state of the universe and what is the desired state of the universe. Every custom type will have usually one custom controller that is attached to it. Package up all of those multiple controllers and multiple custom types together, and you end up with an operator. But okay, enough about the ideas behind the system. Where's the code? Unfortunately, writing complex operators in Python is doable, but a bit tricky. There's two main projects that are trying to make it easier to write Kubernetes operators in Python. One is called COP, and the other is called MetaController. They're both, however, aimed at relatively simple use cases, and they're pretty early in development. There is also a low-level client library that's auto-generated for Python, but then you have to write all of the custom controller and custom tools, custom type specific stuff yourself, and no one has really written a thing to make that easy yet. So in the end, we decided to go with the more community standard kubuilder and controller runtime libraries, even though those are in Go. I'm going to summarize the things that we wrote in Python pseudocode from here, but if you go and look at my actual repository, which will be linked at the end, it will all be in Go. So be it. So the first problem that we tackled as we were writing our custom operator was the big problem we had with Helm, sequencing and ordering. We added a lightweight state machine to figure out sort of where in the deployment process our system was. The first phase, initializing, covers the setup of databases and other underlying infrastructure, sort of like big global stuff that's usually only done once. And then we had migrations run per version, deploying per version, and then ready, and error when that happens. This is some of this pseudocode specifically around dealing with migrations. This is one of the nice things about writing custom operators, though, and we'll see this a couple of times throughout the talk, is that because this is real code, as opposed to just being a declarative system like Helm or other YAML-based tools, we control it and we can make whatever behavior we want. So it allows very, very careful customization of exactly how migrations work in Django, say, which is subtly different than other frameworks, and lets us very carefully control the behavior of what happens if, say, there's an error during migrations. What do we do? Like, what does that mean? In the case of Django, it doesn't attempt to auto-roll back, for example. So we have to understand that there was an error and flag that to an operator, as opposed to some other frameworks where it'll auto-roll back and you just try again. I put aside Celery Beat earlier, so now's a good time to pull it back out. There's two problems with Celery Beat for anyone that runs it. The first is that if you run 2 copies of Celery Beat, it's the thing that schedules all of your scheduled tasks, so basically it's like cron for Celery, and if you run 2 copies of it, your scheduled tasks just run twice. If your tasks are all perfectly idempotent, that can sometimes be okay, but it's still gonna be a load increase, and usually you'll end up with 1 or 2 tasks that if they're run twice, bad things happen. It's certainly easy to happen unexpectedly, and people do not understand why. The second problem with Celery Beat is it is a stateful tool. It stores a bit of information for every task, like when it was run last. By default, it stores that in a file on the local file system. There's a tool called Django Celery Beat that puts into Django's SQL database, but that's a lot of write load. Like, we have a couple dozen tasks running every, I think, 5 seconds. And so that would just be an enormous amount of write load on our SQL database that we didn't really want. So this brings me to a tool that I hope everyone will now be able to use called Celery Beatx. Beatx solves both of these problems. The first phase, it does locking between multiple instances of Celery Beat. So if you have more than one running, only one will be active. And it also allows storing the Celery Beat state into your cache backend, so either Redis or Memcache, which is usually a lot better for live data like that than SQL. There is a catch, though, which is it is Python 3 only, and if you remember, my app is not yet on Python 3, so I actually can't use this, so be better than me, use Celery Beatx. Otherwise, you gotta deploy it on a stateful set, and it's kind of a pain in the ass. So again, with pseudocode, but this is another example of why it is nice to be able to control at a code level what is going on during our deployment. This is an example of we auto-generate the passwords for all of our database users as we're creating them automatically, and so we wanted to feed those passwords back into Django. I mentioned before that we put all of our config into YAML, so we want to read the dynamic passwords for our database users, both SQL and RabbitMQ. We put those into the YAML dynamically, render some YAML, put them back in a secret that gets mounted into our container, and then the settings.py can read it as if it were a file. And because this is in the controller, anytime anything changes, so if we want to rotate all the passwords, we tell the system to update the passwords, and then it'll cascade through the system naturally. So that covers the underlying tech. What about workflow? That's just as important as having good deployment systems, having good deployment workflow. Our original was fairly simple, deploy.sh. It just wrapped running Ansible. Pretty simple, repeatable, but it had some issues. The biggest ones were that there was a source of truth mismatch, and that because convergence was both partial and manual, things could drift over time. With the source of truth, the idea of mapping out sources of truth is to figure out where in your system a given piece of data is authoritative. So for example, with our Ansible code, that was authoritative in Git. Git defined what was the correct way to configure a system. But where did the information about the versions that should live on each server go? In our case, that didn't really go anywhere. It was basically authoritative on the running systems themselves based on what version was git cloned onto them. So that we had no like centralized overview of what versions were where, and there was no easy way to like back up and restore that information because it was just what was on the machines. This also comes up if you're using Jenkins parameterized build jobs for doing deployments, same problem. The thing that records where your versions live is Jenkins build parameters, which isn't a thing that you can easily like review and back up and restore. And then the related issue of drift, that because doing a push becomes a manual action, it is possible for things to be missed and to slowly drift over time. Usually in our case, this meant an old test server sitting in a disused corner of our AWS account that was unpatched for months or years. So GitOps. The central idea of GitOps is that Git is your only source of truth. All information, configuration, code, everything has to live in Git somewhere, somehow. And then you have some automation that is reading configuration and infrastructure changes out of Git and affecting them onto the universe. This approach gets you a lot of great things. Because the full state of your configuration is reflected in Git at all times, the automation can continuously clean up that drift. So if you make a change to your deployment system somehow, it will take effect across every machine simultaneously. That also means that you can take down all the fraud simultaneously, so make sure you have good tests, but it is nice that things will never be out of sync. It also means that if there's an emergency, you have all of your stuff in one place. I can push one button and restore my entire infrastructure because it's all in one place, and that is the authoritative source. It also helps just bringing a more code-based workflow to operational changes. You get things like code reviews and commit messages and things like that. It can be used as a kind of discount audit log of seeing who made changes when and hopefully why. But it's not perfect. The biggest friction we've had in switching our teams to GitOps is frustration that they have to get what they feel are minor operational changes fully through a code review process. We're currently using the GitHub branch protection rule system, and it's got some flexibility in determining who does reviews, but not a lot of flexibility in what should be reviewed. So our goal is to eventually try to replace that with a custom review management system, but we haven't yet built that, so there's been a lot of frustration from some of our team members. Also, we've had some team members that are engineering adjacent. They're not working in code day to day, but they do need to interact with the deployment system, and they didn't necessarily have GitHub accounts. They didn't know how to use it very well, so we've had to guide them through that. It's been okay since then, but it was definitely a thing that we sort of forgot to factor in, is that there are people that don't sit in GitHub all day. And of course, if your team members don't fill in good commit messages or don't review things consistently, then that data source is not going to be very useful. We do have a lot of update foo.yaml as the commit message, which, so it goes. So put it all together and we get a new end-to-end workflow based on GitOps. We use a tool called Argo CD to do the critical watch your Git repositories and sync them into Kubernetes, but there's a lot of tools around there. Find one that works for you. The general idea is to have GitHub be, or Git in general be, the source of truth. All right, some bonus things, because we do have a few extra minutes. Second piece of the puzzle that we built was a CLI tool to handle common tasks that our engineers would come up with. The first two of these, for example, are just wrappers around the kubectl exec command line tool to give you a bash shell or a Python shell on a given instance of the application. The last one is a wrapper around pSQL to pull the right database information, user, password, hostname, and just feed it into pSQL so they didn't have to go find that every time. We've been adding more debugging assistance tools to it over time, and it's been generally, I think, well received. We took a cue from Homebrew, and we added a command to our thing to both examine environmental issues and potentially auto-fix them if it knows how to. This has been very helpful in just getting more people set up on the new platform. We can just tell them, hey, please run Radical Doctor and paste me the output. This is still mostly in testing. We haven't rolled it out to production yet. As an ops person, I like command line tools, so I'm cool with just like kubectl describe as my interface to a lot of things, but not everyone on all of our teams feels the same way, so we started to build a fairly simple read-only user interface so that they could navigate to things via the web and see nice graphical pretty things. So while our Django deployment logic in this thing is definitely fairly tailored to our needs, it's still pretty general Django, and it is all open source, which is nice. It is not particularly well documented, but it is open. If you want to go look at it, steal ideas, steal whole sections of code, that is highly recommended. And yeah, thank you so much for having me. Any questions?
Hey, thanks for the talk. It was really insightful. One of my biggest fears from moving to a PaaS like Heroku to a more flexible Kubernetes environment is Heroku does so much for me with managed Redis, Postgres. They tell me when maintenance needs to be done, they do it. I guess my question is, have you still kept that managed, or are you managing that yourself?
For Postgres, we use RDS. For RabbitMQ, we use Cloud MQP. Redis in particular, we decided to run ourselves because Amazon does offer Elasticache Redis, but it is remarkably expensive, and Redis is pretty easy to run. I will point out that you can actually use Heroku Postgres without using Heroku. They don't super advertise that fact, but if you're on Amazon, it's running in Amazon. You can just keep using Heroku Postgres if you like it.
I like that, yeah. Okay, thank you very much.
Hi, yeah, thanks for the talk. I have a question, as someone who's tinkered with Docker and, kind of been getting into these types of technologies, maybe even using them in production, how would you recommend someone diving into Kubernetes as kind of the next level?
Really just what I showed in the talk of start writing some YAML. Pick an application. The one I generally recommend is WordPress because it is really it's got a slick installation process, and there's 1.5 million guides to every possible flavor of WordPress thing you could want to do. So just start writing some big YAML files to deploy it, deploy, I guess, MySQL if you're doing WordPress, deploy a WordPress container. It's got a fairly well-polished Docker image already, so you don't have to make that yourself. And just try deploying stuff. GKE is really easy to get started with, and if you remember to shut it down when you're done using it, it's pretty cheap. So yeah, that's where I begin.
Hey, I was just curious, when you were in the section regarding GitOps and you were talking about getting people engaged in that process, you said that there was difficulty with people who weren't engineers being engaged with that process. Who that's not an engineer cares enough about your deploys to get involved in that anyway?
Mostly the product management team and the release management team, all of whom are not necessarily, the release management team has some engineers on it, but it also has more PME kind of people that do want to be involved. They want to see when deploys are happening because it's part of their checklists, but they're not living and breathing in GitHub. One of them had a GitHub account but hadn't logged in a couple years. A couple of them had never had GitHub accounts, stuff like that.
So when you, as you finish up that more friendly UI, is the intent that a lot of those people would just be pushed towards that because it's mostly about communicating to them, not necessarily them contributing?
Yeah, probably. If they want to be able to see system status, and we're also working on sort of custom tools, especially for the release management team. They really want to be able to see not just what version is in one place. They want a big overview of which given what versions are in prod and where are they. But because everything is just in YAML files, it's pretty easy for us to just write a little script that generates them a nightly report or whatever and emails it to them. So a mix of that web UI and just writing little custom integrations that either talk to the Kubernetes API directly or just read and parse YAML files out of GitHub.
Cool, thanks.
Awesome. Thank you so much, and enjoy your break.